This lesson we're going to learn one of the most important things of the entire section or entire chapter, which is transformations of functions and using that to sketch graphs. Doing the XY chart is way too time consuming for most graphs that you need to put together. So what we need to do is know what the general shape of a graph is because of what kind of function it is, which we learned previously. Then if we start to alter that function, how does it alter the shape? So what I have here are three functions. I have f of x equals x squared. We should know what that looks like. G of x equals x minus 2 all squared, and h of x equals x squared plus 2. Each one of these is a squaring function here, here, and here, but they're altered in different ways. So let's think about the first one. F of x equals x squared. What does that look like? Well, it's got this parabola shape to it, right? It's got this vertex, this low point at 0, 0, and it looks like this U. Now let's look at g of x. Well, in order to draw g of x, just to get started, we'll do it the old way. We'll do a table. So what I'm going to do is I'm going to plug in some x values and figure out what the y values are. So I'll plug in 0, 1, 2, 3, 4 as some of my x values. Now the shape should still be the same shape as the original square. It should be a parabola, but there's a change to it. So let's see what happens. Plug in 0 for x. So here's my x. If I plug 0 in for x, I'm going to get negative 2 squared, which is 4. If I plug 1 in for x, I'm going to get 1 minus 2, which is negative 1 squared, which is 1. 2, I get 0. 3, I get 1. 4, I'll get 4. Okay? Again, I'm plugging them into this function, minus 2, square it. So if I connect the dots, if I do this graph, what's going to happen? Well, 0, 4 here, 1, 1 here, 2, 0 here, 3, 1, 4, 4. Remember, the shape should be a U shape. So what does it look like? Well, it looks like this. Now, how is that different from the original graph? Well, the change from the original graph is we moved that direction. How much? 2 units. Now, what did we do to the function? We subtracted 2 inside the square, okay? And if I subtracted 2 inside the square, it moved it to the right 2 units. Well, what do you think if I was to add 2 inside the square? What would that do to the original graph? Well, what it would do is move it 2 units to the left. And my graph would be over here at negative 2. So if you know how we altered the function and how that alters the graph, I no longer have to do this table to draw my graph. I know what the original graph is supposed to look like, and I know how I altered it, and now I can draw my final picture. Okay, now let's look at this one. X squared plus 2. Now there's a major difference. This one I'm adding 2 after the square. Here I was doing my minus 2, or even I could have done a plus 2 inside the square. This one moved it left and right. What's going to happen here? Well, what we can do is do another table. Plug in some x values. Let's say negative 2, negative 1, 0, 1, 2. These are just random x values. Now, they're not completely random because I know what's going to happen to the graph and I'm trying to show you. So they're not completely random, but they could be completely random. So I plug negative 2 in, square it, add 2. I get 6. Negative 1 squared is 1, plus 2 is 3. 0 squared plus 2 is 2. 1 squared plus 2 is 3. 2 squared plus 2 is 6. So I go to draw this graph here. Negative 2, 6. Negative 1, 3. 0, 2. 1, 3. 2, 6. Connect the dots. The shape should still be a U shape. Okay. And it is, but how is that different from the original graph? Well, if you look at the original graph and you look at the final picture, What's the difference? The difference is I am up 2 units. So here I added 2 after the square, and I went up 2 units. Here I subtracted 2 before the square or inside the square, and I went right 2 units. So the square is really the function. So if you do something inside the function, add or subtract, you should move to the left or right. If I add after this function, after the square, I should move up, and if this was a minus, what would happen? I would move down. So here are our general rules. If we look at this and say, okay, here's our function. We look at these values, C and D. C and D are positive real numbers. These are going to be the things that I use to change my function. So if I add or subtract C or add or subtract D, how's that going to affect the overall graph? Well, let's look at the first one. Here I am subtracting C inside the function. Inside the function, you see it's inside the parentheses, so I'm subtracting C inside the function. What I get is a horizontal shift, C units to the right. Okay? If I add inside the function, again that's inside the function, it's inside these parentheses, I have a horizontal shift, C units to the left. Which is kind of opposite of what you think should happen, right? If you use common sense, you would say, well, if I'm subtracting and I have to move left or right, you would probably think move left. But it's kind of the opposite here. X minus C actually moves it to the right. X plus C inside the function moves it to the left. Now, vertically, it does kind of exactly what you think should happen. Now, this is a minus D, and that's outside the function. If you look at it, here's my function. This is outside the function, outside the parentheses. I'm subtracting D. What I have here is a vertical shift downward, and if I add D outside the function, I have a vertical shift upward. So if I gave you a function, I said, okay, here's my function, f of x equals the absolute value of x plus 2 minus 3. How do you think this graph will be affected? Well, first, what's the original graph going to look like? An absolute value, an original absolute value, say g of x equals the absolute value of x, would be the shape of a v. The point of the v would be at 0, 0. So how is this graph different? Well, I have a plus 2 inside the function, inside the absolute value, and a minus 3 outside. So if I use a plus 2 inside, that's adding 2 inside, I should have a shift to the left. So this should go left 2 units, and then I have a minus 3 outside. Well, that's outside the function, I'm subtracting it. So that should be a downward movement, so I should go down 3 units. So I should take my original absolute value, which is this v, and I should go left 2 and down 3, and my v would be there. Okay? So this is how these transformations change our functions, which will make graphing so much easier. Now we don't have to do that XY chart. If I know what the original graph should look like, this is an absolute value, it should look like a V, and I know how that V is then affected by these changes, I can then put my graph together fairly quickly. Now it's not 100% accurate, but none of our graphs are 100% accurate. What we just have to do is draw the best graph we can do in the least amount of time. So here's an example. Given f of x equals x cubed, describe the shifts of the graph of f generated by the following functions. First one, g of x equals x cubed, x plus 1 cubed plus 1. So what's our general function? A cube. Know what that shape looks like. A general cubic shape looks like this. Okay? X-axis, y-axis. That's what our cube looks like. So now we're going to change that. So what's happened here? Well, I have a plus 1 inside the cube and a plus 1 outside the cube. That affects the graph how? Plus 1 inside. Plus 1 inside is a horizontal change. Since I'm adding 1, I'm going to move to the left 1 unit. Remember, that's kind of opposite of what you think should happen. Plus, you would think move to the right because that's where the positive values are, but it's opposite. So plus 1, I'm going to move to the left. And this plus 1 outside the cube, I'm going to move up. So I'm going to take my basic cubic function, which looks like this. And I'm going to take this cubic function and move it left 1 and up 1. So this center point is usually the easiest point to work with. And I'm going to take this center point, I'm going to move it left 1 and up 1. And I'm going to place it right here. That would be left 1, up 1. Now that's the center of my new graph. So I'll just try and trace my cubic shape as best as I can through that point. And I think your best bet is to label that point, -1, 1. Why do I want you to label that point? Well, it's a good way to check to see if you did this right. If I plug this x value into this function, I should get this y value. So if I find g of -1, I should get 1. If I don't, then I move the graph in the wrong location. Well, think about what's going to happen here. I'm going to get -1 plus 1 cubed plus 1. Well, this is going to be 0 cubed, so 0 plus 1 does give me 1. So if you look at it, it does work. -1 gives me 1. So -1, 1 is a point on my graph, and that's where my graph's going to be located. Let's do another one. So if we look at h of x is x minus 2 cubed minus 4. Again, another cube, so it starts with a general shape that's the same. But here I have a minus 2 and a minus 4. Minus 2 inside the cube, minus 4 outside. Inside is horizontal. Now it's minus, so that's going to move me to the right. And a minus 4 outside, that's going to move me down. So if I look at my graph, here's what my general cube is going to look like. Goes through this 0, 0 point, but now I'm going to go to the right 2 and down 4. So this is where I'm located now. So that point is 2, -4. So I'm going to draw my graph through that point. Try and do as best you can with your cubic shape. It doesn't have to be perfect. These are just estimates, but that's going to be what my graph looks like. So that's the graph of x minus 2 cubed minus 4. That is much easier than having to do any other method of graphing this particular function. But you gotta know what the original function looked like, the cube, and then how these two parts change that graph. Another way we can change the graph is reflecting the graph, flipping it over in some direction. Well, we could flip it over two axes, the x-axis or the y-axis. Now, this is going to happen when we introduce a negative multiple somewhere into the problem. Now, there's two different ways we can do this. We can have a negative outside the function or inside the function. Now this is a multiple, so I either multiply the entire function by a negative, the entire outside of the function by a negative, or I multiply the entire inside of the function by a negative. If I multiply the entire outside of the function by a negative, it's going to reflect over the x-axis. It's going to become a mirror image over the x-axis. If I reflect over the y-axis, that would be when I put a negative inside the function. So just like with the changes horizontally or vertically, it matters what happens inside or outside the function. Am I adding or subtracting inside? Am I adding or subtracting outside? These are the same. The reflections are, did I multiply by a negative outside, or did I multiply by a negative inside the function? So here's an example. Given f of x equals x cubed, describe the reflections that are happening here. So if you think about this, the cube is my function. This negative is inside the cube, so that should be my reflection over the y-axis. If I look at this other one, h of x, this negative is technically outside the cube, so that should be a reflection over the x-axis. Now sometimes these things will generate the same graph, sometimes they'll generate different graphs. It all depends on the function and the type of reflection that you're doing. So if I drew this first one, g of x, what I'm going to do is I'm going to say, alright, well, I have my x cubed, right? So if I look at my x cubed, it looks like this. What I'm going to do is I'm going to reflect it over the y-axis. Remember, negative inside, y-axis. Well, if I flip this thing over the y-axis, it's going to flip this direction. Okay? So my new graph will look like this. That's my graph flipped over the y-axis. Then what I'm going to do is I still have this other change out here, which is a plus 3. Plus 3 outside the function is going to move it up 3 units. So if I'm going to move it up 3 units, my final picture up 3 units will be right here at 3, will look like this. Now this is pretty much a mess to have to look at, so you really should only draw your final picture. And once you draw your final picture, you can kind of see what it looks like. So this is what my final picture will be. But that was reflected over the y-axis and then up 3 units. Let's look at this one. This one here, I have a negative outside the cube. So a negative outside the cube is going to flip it over the x-axis because that's a negative outside the function. So if I flip that over the x-axis, well, I take my original curve, that's my cube. If I flip it over the x-axis, that means it's going to flip this way. Whatever's below goes above, whatever's above goes below. So the graph I'm going to get is this graph, which just so happens to be the same graph I would have got if I flipped it over the y-axis. Then I still have the second part, which is up 3 units, 1, 2, 3. I put my final graph right there, and I actually end up getting the same exact graph I got before, which happens sometimes. Sometimes the reflection over the x-axis is the same as the reflection over the y-axis. Sometimes it's not. So you need to make sure that you flip the appropriate way and move the appropriate way. Now, as far as order goes, it doesn't matter which way you move first. You can move horizontally first, or you can move vertically first. It doesn't matter. But what does matter is when you combine reflections and the movements. My common rule that I think students should follow in most cases is flip first, move second. Again, that's flip first, move second. Now, the only time I say you shouldn't follow that rule is if the problem tells you not to follow that rule, because the order is important. If the problem says move your graph 5 units to the right, then flip over the y-axis, then you follow the steps that the problem says. But if you're just looking at a function like we are here and here, you should flip first, move second. So let's look at this problem. This problem's a little different in that you're not actually graphing this particular one, but you're writing what the function would be after you make the changes. So it says, write the equation of the graph f of x equals x to the 4th that is reflected along the x-axis and moved 2 units upward. So it's reflected over the x-axis. That means there's a negative multiplied. Where is it multiplied? Outside the function. Then it's moved 2 units upward. And look at the order. It said reflect first, move second. So it's exactly the way it should work. So I say, okay, here's my function f of x equals x to the 4th. If I multiply by a negative outside the function, that's going to reflect it over the x-axis. Then if I move it 2 units upward, I should add 2 to that function. So if I reflect over the x, move it 2 units upward, this is what the new function will look like. So that's the equation of the new function. No graph is necessary here. The question said just write the equation. Now, the order is important because if I switch this order here and here, and I say move up 2 units and then reflect over the x-axis, well, think about what that would be graphically. I take an x to the 4th. Well, what does an x to the 4th look like? We haven't really looked at that yet, which isn't so big a deal when it comes to this example, but if you have to graph it, I guess it is a big deal. The key is x to the fourth. It looks like x squared. All these powers, whenever they're an even power, will look like a square. Whenever they're an odd power, look like a cube. So x to the fourth looks just like an x squared. There's some small differences in the curve, but generally it's a parabola shape. So if I said, let's switch these two things around. Let's move 2 units upward first. So now I'm here. And then let's reflect it over the x-axis. Well, if I reflect it over the x-axis, the whole thing's going to have to come down here. So now it's going to actually be down here 2 units, and it's going to look like that. Well, that's very different than if I reflected first and then moved up. Think about it. If I reflected first, I would look like that. And then if I moved up, I would look like this. That graph and this graph are very different. Totally different location. So when you change the order, it makes a huge difference. So what's going to happen there? Well, if I think about what that was, and let's look at that final picture again. It was 2 units down and it was flipped over. So what's going to happen is it's going to be f of x equals negative x to the fourth minus 2. Because I'm really actually down 2 units. Even if I said up 2 units, then flip over the x, okay. Even though I said up 2 units then flip over the x, because I went up and then flipped, because I did my flip second and not first, I'm actually going to be down 2 units. So be very careful when the problem tells you to do something, what order it tells you to do it in. If it doesn't tell you to do it in an order and you're just looking at a function, flip first, move second. But if you have a problem like this where it's telling you what to do, be very careful in terms of how they tell you to move the function and what order it is. Because even though it says move up, in the end your graph might be down. Because if I go up 2 units and then flip over the x-axis, I'm actually down 2 units. Let's get a little bit more practice with these translations. So let's graph these couple of functions. I have square root of x, square root of x minus 2, square root of x plus 2, that one's outside the square root, negative square root of x, and I'll add one more to this list, the square root of negative x. So if I look at this, I say, alright, well, let's look at the first one. F of x equals the square root of x. So what does that graph look like? Simple, basic, square root of x. That's it. How about f of x equals the square root of x minus 2? Well, that minus 2 is inside the root. So that's going to be a horizontal shift to the right. So I'm going to go right 2 units, and I have this graph there. That's that one. How about the square root of x plus 2? In that case, the plus 2 is outside the square root. Well, outside the square root, I'm going to go up 2 units because I'm adding 2. So I go up 2 units and I'm there. So these are all compared to this original graph. Right 2 units, up 2 units. How about f of x equals negative square root of x? Well, in that case, that one is a negative outside the function. Outside the function means I flip over the x-axis. So if I flip over the x-axis, I'm going to look like that. And that's my graph there. How about f of x equals square root of negative x? Well, a lot of students will look at this and say, well, I can't even do this one because I can't have a negative inside. Well, you can have a negative inside. You can't take the square root of a negative value, but there can be a negative there because all I have to do is plug in x's that make this thing positive. Well, if I plug in a negative x and I multiply it by a negative, I now have a positive inside the square root. So I can do this, but think about it. A negative inside the square root or inside the function means I should flip over the y-axis. So my graph looks like that. And look at the x values that I'm using here for this graph. They're all negative x values. If I plug a negative in here, I multiply by a negative, I'm going to get the square root of a positive. So that's what my graph looks like there. Now there's one more I want to show you that's a little tricky. So let's get rid of some of this. And it has to do with the reflections and the horizontal translations. And there's a really small trick that you need to worry about, but as long as you follow this general rule, you'll be okay. So how about this? F of x equals the square root of negative x plus 2. So what do you see? There's two things you see here. You see this negative and this plus 2. So there's a negative inside, so you would think flip over the y-axis, and a plus 2 inside, which normally you would think move to the left. But there's a problem here. If I did that, if I flipped over the y-axis and then moved to the left 2 units, I would look like this. This point would be negative 2, 0. Now remember, I should be able to plug that point into my function. Plug this x in, I should get this y. Well, what if I found f of negative 2? F of negative 2 is going to be the square root of negative 2 plus 2, which gives me the square root of 2 plus 2, which is the square root of 4, which is 2. I don't get 0, which means I moved it wrong. Well, where did I screw up? I messed up in one way, and it's the way that I looked at it. And the key is the negative part. In this case, I'm looking at it as the x is multiplied by a negative, but I really have to do is look at it as the entire inside is multiplied by a negative. Well, if I look at that way, then it means I gotta factor a negative out of this whole thing. So this becomes x minus 2. If I multiply that negative back in, I would get negative x and a plus 2. But by looking at it this way, I have the whole interior is multiplied by a negative, and therefore I'm still going to flip it over the y-axis, but now I see a minus 2, which means move it to the right. And now I'll be in the right location. So if I flip it over the y-axis, which is this, and then move it to the right 2 units, I'm now looking at this function, and the point that I'm at here is 2, 0. Now if I plug 2, 0, or 2 into the function, I should get 0. If I plug 2 in here for x, I get minus 2 plus 2 gives me 0. Square root of 0 gives me 0. So you see, I am in the right location, but it was all about the way I looked at the function. Whenever you have a negative inside your function, so again it was negative x plus 2. Don't look at it as the x is multiplied by negative, but you have to look at it as the entire inside of the function is multiplied by a negative. Then you'll be always moving it in the right direction. Let me give you one more. So if I said, how about f of x equals the absolute value of negative x minus 3. Would I be moving this to the left or to the right? Well, I gotta look at it in the right way first. This is a negative multiplied inside the function, but that's only times the x. If I multiply it by the entire interior of the function, this would become x plus 3. Now I say, okay, plus 3 inside my function, move left. Okay, now I'll do my reflection first, but that would be over the y, but I'm moving to the left and not to the right. So that's the way you need to look at these functions. Another kind of transformation that you can come across is what we call a non-rigid transformation. All the transformations we just looked at didn't affect the curve of the graph. It was like a rubber stamp. You picked the function up and you put it down in a new location. But you never really changed the shape. You just changed the location of the graph, either by horizontally or vertically shifting it or flipping it over. A non-rigid transformation will alter the shape of the graph. Okay? Now generally the shape will still be the shape that it started with, a V or a U or whatever, but the curve will be, altered in that it'll be stretched in some direction. So that happens when you have a multiplier outside your function, or even inside your function, but we're only going to look at multipliers outside the function. So this k value right here, k times f of x. So whether that k value is bigger than or less than 1 is really going to be the determining factor of how your graph is altered. So if k is greater than 1, it's going to be a vertical stretch, which means if I stretch my graph out vertically, if I pull it in either direction vertically, it's going to actually end up looking skinnier overall. If my k is less than 1, then my function's going to be vertically shrunk, which means it's going to look wider overall. If I compress something down vertically like this, it's going to have to come out and be wider this way. It's going to pop out this way if I push it down vertically. So vertical stretch, it looks skinnier. A vertical shrink, it looks wider. Okay. Now I have these absolute values in here. There's a reason, because this multiplier outside does two things. One thing that the multiplier outside does is it can flip your graph over. Right? If this k outside was negative, it will flip it over the x-axis. So if I want to sort of ignore the flip part of it, I should ignore the sign of k, and by ignoring the sign, really what I can do is take the absolute value of k. So if that absolute value of k is bigger than 1, I stretch it vertically. If absolute value of k is less than 1, then I'm going to shrink it vertically. Now this really doesn't change the way you graph things. I mean, if I think about it, I have a parabola. Here's my standard parabola. If I stretch it in this direction and this direction vertically, what's going to happen is I think about grabbing this piece and grabbing this piece and start pulling them up. If I start pulling them up, what's going to happen is my graph is going to end up looking skinnier overall. And that's what a vertical stretch does, is it makes the graph look skinnier. If I take this and I affect it the other way, I compress it. So think about like taking it and having a press here and a press here, and I start squeezing this down this way. Well, if I start squeezing this down, this point's going to come down lower here, and my graph is going to actually start looking like this. So my graph looks wider. And that's going to happen depending on the k value. If that number in front is bigger than 1, if that number in front is less than 1. This is how it's going to affect the graph. But the location is still the same location, which is really the most important part. So let's just look at two examples. Compare the graphs of the following functions. We have f of x equals x squared. Okay? 4x squared and 1/4 x squared. The key is the multiplier. Here the multiplier out in front is bigger than 1. And here the multiplier is less than 1. So this one's going to look skinnier, and this one's going to look wider. Okay. Then the normal x squared. So I go, alright, well, if I draw all these on the same plane, here's my x squared. This is what my 4x squared is going to look like. So that would be 4x squared. And then let's change the color. The 1/4 x squared is going to look like that. This one being my x squared. So you see them all compared to one another, but they're all just parabola shapes still in the same location with their vertex. Now, the one thing that's going to happen here is if you don't know what the original graph looks like here I put them all in the same plane. If I don't know what the original graph looks like, how do you know that it got skinnier or wider? You kind of don't. So if I said, all right, draw f of x equals 1/5 absolute value of x. All right, so the multiplier out in front is 1/5, smaller than 1, so that should be wider. So I draw my absolute value of x wider. Well, is it wider? Is it not wider? Well, there's no way of knowing unless I compared it to the original absolute value of x. So these non-rigid transformations are not really going to affect the way you graph something. They're just going to affect the graph if you compared them to the original. But if you're never comparing to the original, how do I know that this thing got wider than the original one? Well, I don't, because my graphs are not perfect at all. Like we said before, all our graphs are estimates. So unless I said, okay, here's what the original absolute value looked like, here's what the wider one looks like, that's the only way I'll know, you know, if it's wider or not. But if I just said draw 1/5 x, or 1/5 absolute value of x, and I did this, I would never know that it was wider without just saying, hey, this one got wider.